Greetings, AP Chemistry students. Yesterday we were working with Lewis structures for substances that, generally speaking, follow the octet rule. But there's a whole nother category of elements, which are substances that don't always follow the octet rule. They usually do, but they sometimes don't. So the first set we're going to look at are some that go under the octet rule. So boron typically forms structures with only 6 valence electrons instead of forming double bonds, and beryllium forms structures with only 4 valence electrons. The key one to focus on for this is boron. For instance, if we're working with the compound boron trichloride, boron will bond with 3 different chlorines. If we look at the valence electrons, it's boron has 3 plus 7 plus 7 plus 7. We add them up, we get 24 valence electrons or 12 pair. So we start drawing in the electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we just leave it exactly like that. We don't make double bonds and draw resonance structures with boron. Now, where things get interesting with boron, because it does that and it's got this empty spot available, is if you take something like NH3, which has those free electrons there, then what can happen is NH3 and BCl3 can form a bond just by plugging that pair of electrons in right there and making a much larger molecule. So that's your example of going under the octet rule. That's a less common exception. The thing you'll see a lot more often is that elements that are in periods 3 or above. So starting with sodium, but really sodium doesn't matter because we're talking about covalent bonding generally. So primarily starting with silicon, phosphorus, sulfur, chlorine, and all of these elements down here, they can exceed the octet rule because they have available d orbitals for bonding. Because when you're following the octet rule, the reason it's 8 valence electrons is because you have one s orbital and you have 3 p orbitals that hold a total of 8 electrons. But starting with the third energy level, you also have those d orbitals that are available and just sitting there with no electrons in them, and they can contribute to bonding as well. So these elements can go over. They can have more than 8 electrons around them. Usually they can go up to 10 or 12. Now, if you can draw a structure that doesn't violate the octet rule, that's the preferred option. But sometimes you have to violate the octet rule, and these elements can. So here are some examples. We've got sulfur hexafluoride, phosphorus pentachloride, the triiodide ion, chlorine trifluoride, xenon trioxide, radon dichloride, and iodine tetrachloride. So I'm going to draw these out with you, and then we're going to come back to these molecules once we start talking about shapes, because that's going to be the next leap that we take. So if we look at SF6, let's see. Sulfur has 6 fluorines around it. So we're going to go 1, 2, 3, 4, 5, 6. And we start adding up electrons. We've got 7, 14, 21, 28, 35. And then we've got 42 plus 6, 48 electrons. That's a lot. 48 valence electrons or 24 pair. So we start drawing in these electrons. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. I missed a pair there. Okay, so that's how we draw this. This is SF6. So it covers all of our bases. We've got all the fluorines are following the octet rule because fluorine being in period 2 has to follow the octet rule. And then sulfur has 6 pairs of electrons or 12 electrons around it, and sulfur can do that because it's in period 3. So sulfur hexafluoride does exist. Selenium hexafluoride could also exist, but oxygen hexafluoride does not exist because oxygen does not have those d orbitals. Oxygen's in period 2. It cannot exceed the octet rule. You need to make sure you are aware of that fact. We'll look at phosphorus pentachloride. We've got phosphorus, and then we've got chlorine, 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 and chlorine. We add up our electrons, 7, 14, 21, 28, 35, plus 5 is 40 valence electrons, or 20 pair. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20 pairs. Then we get to the triiodide, which is an interesting one. So we've got 3 iodines. So it's 7, 14, 21 electrons, but it also has a -1 charge. So that's 22 valence electrons, or 11 pair. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got an extra pair. And so what we do with an extra pair is we just stick the extra pair on the atom in the middle. So this iodine has 3 lone pairs of electrons around it. And once again, whenever you draw Lewis structures, save the element in the middle for last when you're putting the electrons on it. And then if you have extra electrons, just dump them on the one in the middle. Right. So let's take a look at the other ones here. We've got chlorine trifluoride. We've got chlorine, fluorine, fluorine, and fluorine. Take a minute and see if you can draw this yourself. And then unpause the video and come back and watch me draw this. So for drawing this one, we've got 7, 14, 21, 28 valence electrons, or 14 pair. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you just put the extra pair of electrons on the chlorine. Then we've got xenon trioxide. And radon dichloride. And iodine tetrachloride. So take a minute and see if you can draw these yourself. Okay, so for the xenon trioxide, xenon has 8 electrons, plus each of our oxygens has 6. So that's going to give us 26 electrons. So we draw, or 13 pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That one doesn't actually violate the octet rule at all. It's just a novelty one because it's got a noble gas in the middle of it. Then we have, over here, we have radon dichloride, which has 8 plus 7 plus 7. So that's 22 electrons, or 11 pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then for iodine tetrachloride, we have, this one gets really interesting. We've got 35 electrons. So this one, or that gives us, if we look at pairs, that's not an even number. That's, what's that going to be? 17 and a half pairs. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, plus an extra electron. So you just stick that extra electron, that's called a free radical, we just stick it on there as well.